Hi and welcome to this video, and this lesson I'm going to be covering bonding and properties. We'll look at two specific properties as we go through, and we'll fill out this table, and this is a really important table to get to learn, and that is, I'm just going to move these across a bit. First of all, melting points. And we can say or boiling points, because if it's got a high melting point, it's going to have a high melting point, and vice versa. And electrical conductivity. So does it conduct electricity? So the first thing we'll look at is some metallic bonds. I'm going to decide will metallic bonds have a high melting point or a low melting point? Have a look at metallic bonding here. I've got my nice lattice with my delocalized electrons. So I've got positive metal ions, and they're attracted to our delocalized electrons. So in order to get this to melt, or to become molten, we have to break down the attractions that are holding it together as a solid. So what's keeping it is this lattice, and that is the attraction between the positive metal ions and the delocalized electrons. Now there are a lot of these attractions. There's sextillions and sextillions of the positive metal ions in a few grams of any metal, and they're attracted to the delocalized electrons. So these attractions are going on all the way through. So in order to break down this attraction between every single metal ion, in order to get it to melt, at least most of them, you need generally a lot of energy. Now there are a few metals that you don't need so much energy for, such as mercury. But in general, metals, we could say, have a high melting point, which is lucky for us. If steel didn't, then we'd have it just buildings melting left, right and centre as soon as you got a hot day. So metallic bonds generally a high melting point. Let's have a look at its electrical conductivity. Now, in order to conduct electricity, it's got to have one of either two things. It's got to either have ions that can move or delocalized electrons. Now, as a solid, all its ions are held in a lattice, so the ions can't move as a solid, but it does have delocalized electrons. So it does. And because it has these delocalized electrons, it can therefore carry charge. The electrons can move through, they can carry the charge through any metal. So it won't matter whether solid, liquid, it'd have these delocalized electrons, it can conduct electricity. So metals generally have a high melting point and can conduct electricity. Let's have a look next at ionic. I have to apologise for my diagrams. They get worse as I go through. So trying to draw a 3D diagram of ionic bonding isn't too easy, but you should be familiar with this lattice to represent an ionic bond. We could say here that the black represents sodium ions and the red Cl-. So what we've got here, these black lines represent all the different ionic bonds. So we draw, or we'd write, the formula of an ionic compound as NaCl. Now, because it's ionic, what that means is for every one sodium there's one chlorine, but there are literally trillions and billions and sextillions of these sodium ions attract to these chloride ions. So similar to metallic bonding, in order to get these to melt, you've got to break down lots and lots of these bonds, and that requires a lot of energy. So ionic, in order to get to melt and boil, you need a lot of energy, so they have high melting or boiling points. What about electrical conductivity? So if we go back to our ionic bond, we said earlier that in order to conduct electricity, it needs either ions that can move or delocalized electrons. Now, there are no delocalized electrons. All the electrons have been shared. So given from the sodium to the chlorine, they're contained and they're localized, not delocalized. So as a solid, as it would appear here, their ions are all locked into position. There are no delocalized electrons. So as a solid, no conductivity. As a liquid though, if we break down all these bonds, then the ions can move. So we've got ions that can move around. I think liquid, you tend to say it's molten. You'll see either of these two phrases used, or even liquid, molten, or dissolved. But then the ions can move, key phrase, and because they can move, it can conduct electricity. So I go to my table. Have here, we can separate it as a solid. No, won't conduct electricity. As a liquid, or molten, or dissolved, yes, it will conduct electricity. So ionic tends to come up in tests and questions because this takes a bit of understanding to know. You need to know, it would show by answering this question that you understand electrical conductivity and you can apply it to ionic bonding. So it's an important one to know. Next up we have simple covalent. Now, simple covalence, anything where we can, it's covalently bonded and we can write a formula. So you'll see this is CH4, H2O's a simple covalent, CH3, CH2OH, ethanol, that would be simple covalent. We can write down a formula that relates to the compound. So here, CH4, 1 carbon to 4 hydrogens. Now, in order to get this to melt, or to become a gas, we don't have to break these bonds. So before we saw about breaking the intramolecular bonds, but we don't have to break these in order to turn it into a gas. When it's either solid, can you freeze methane? I'm sure you probably can. As a solid or as a liquid, what's holding it together as a solid and a liquid, you'd have, again, trillions of CH4 molecules, is a very weak bond here, known as an intermolecular force. And that's all you have to break down in order to get this to melt or to boil. These bonds in between the molecules, they are very, very weak. So I made a note of that they're really weak. So it doesn't take a lot of energy to do it. So the heat energy we put in, we don't need a lot in order to break that bond. So in simple covalent, we have low melting or boiling points. Methane, the example we've got just here, that exists as a gas. All the other, most metals, with the exception of mercury at room temperature, they're solids because they've got strong bonds. Ionic compounds will be solids at room temperature because they've got strong bonds. Simple covalent tend to be liquids or gases. Those examples I showed you earlier, we talked about methane, definitely a gas, comes out of gas taps in your science lab. Water is a liquid, ethanol, liquid. So simple covalents, low melting and boiling points. Now, do they conduct electricity? Let's have a look at our methane. I'm going to repeat that phrase again. In order to conduct electricity, it needs either delocalized electrons. It does not have any delocalized electrons. It also needs ions that are able to move. Now this has no ion anywhere. There's no in the CH4. It's completely balanced. CH4 completely balanced. So simple covalent are really poor conductors of electricity. So we can say that a simple covalent won't conduct electricity. Now, giant covalent, this is the worst diagram I've got of them all. So in a giant covalent, we have just got, this example here is diamond, each little black dot represents carbon, and they're all bonded 4 times. So each carbon bonds 4 times, and then that carbon bonds 4 times, and then that carbon bonds 4 times, and they link up. Before, in simple covalent, we had 2 different molecules attached together, and we had to break this bond in order to get it to melt. Now this time in giant covalent, we've got the same repeating element or some atom. Sometimes it's 2 elements, as in glass, we've got silicon and oxygen bonded together, but they repeat and repeat and repeat and repeat, and they're all bonded by strong covalent bonds. So covalent bonds generally strongest of the bonds that we look at. So really, really strong. There are no intermolecular forces, none of these weak bonds are there. So in order to get this to melt, you have to break down every single one of these bonds. Just like in the Ionic lattice, you have to break all of those. Lots and lots of them, very, very strong. So giant covalent have really high melting points. Now, do they conduct electricity? In general, no. When we have a look at the giant covalent, there are no delocalized electrons, and there are no ions that are able to move. These carbons aren't ions, they're all covalently bonded, they're all nice and stable. No ions there. There is one that can though. And this is the one exception we look at. And I'm going to draw another terrible diagram. This time I'm going to draw some sheets of graphite. A single sheet's known as graphene. So they sheet on top, and this is sort of a sheet below, and in between they have very weak bonds connecting them up. So once again, terrible diagram. Now graphite is the exception to this conductivity rule, because in between these layers we have delocalized electrons. So graphite can conduct electricity. It's the only giant covalent that we look at that can conduct electricity. So it's just an exception to the rule you'll need to be aware of. So giant covalent in general, no, cannot conduct electricity, but we could put except for graphite. Now this is an important table to learn. And no, one of the ways I would go about learning this, for all this, is to set the table out and then cover up the answers. Then I'll write down and try and fill up the table as it's covered. So metallic, I'll take boiling point. Do I think it's high or low? I'm going to say, yeah, I'll go it's high. Electrical conductivity, I'm going to say yes. Ionic, high. Electrical conductivity, I'm going to say yes. Simple covalent, low. I'll go with yes again. Giant covalent, high. Electrical conductivity, so no, just for fun. I know I've deliberately got some of these wrongs. Now, when I come and check my answers, I can see, can't quite fit it all on, which bits I've got right and which bits I've got wrong. So I can see that I got that right, I've got this correct, I got that wrong. I'll make a note here. So, well, I'm marking the wrong parts. So I'll try that again. So that right, that right, that right. Here, I got it half right. So I'll make a note then that, what did I get? Half right, it was that ionic conductivity. And I might even go and have a look at it right down here. What did I get wrong about that particular question? Why did I get it wrong? And I can go again. I said low here, low there, that's fine. I said that they could conduct when they can't. So again, I'll make a note. I got one part wrong. What did I get wrong? Electrical conductivity in simple covalent. And again, I might go and research and have a look. Why did I get that wrong? What did I get wrong about it? Why did I think it could? Then giant covalent. I've got both right. I could have included for extra marks that graphite does. But that's how I like to revise. It's this idea of covering up and testing myself as much as possible. Good luck with that.